Ever wish you could just like hit fast forward on quantum computing?
Mm,
Skip ahead to the part where these things are actually useful for solving problems in the real world.
yeah.
Well, today's deep dive is going to explore a potential shortcut.
Okay.
Um, we're looking at some pretty cutting-edge research.
All right.
A paper called Leveraging Pre-trained Neural Networks to Enhance Machine Learning with Variational Quantum Circuits.
Wow, that's a mouthful.
I know, right? Don't worry, we'll unpack it all.
Okay.
So basically, the big idea is, what if we could take all the stuff that our classical computers have already learned
Mm-hmm.
and use that to give quantum machine learning a boost?
It's a really fascinating idea.
Yeah.
One of the big challenges we're facing right now is that quantum computers, even the most advanced ones, are still in what we call the NISQ era.
NICQ.
Yeah, noisy intermediate scale quantum.
Ah. Okay.
Basically, they have a limited number of qubits,
Okay.
and you can kind of think of qubits as like the building blocks of quantum computation.
So it's kind of like trying to build a skyscraper with a tiny toolbox.
Yeah, that's a good analogy.
Okay.
And this limited number of qubits, it really holds back the potential of a key tool in quantum machine learning called variational quantum circuits, or VQCs.
EQCs, got it.
And they need a lot of qubits to really flex their computational muscles.
Okay, I see the problem.
Yeah,
So where do these pre-trained neural networks come in?
right.
The paper suggests we can use them to make these VQCs more efficient.
Uh-huh.
But how does that actually work?
Well, think about all the amazing things that AI can already do on our regular computers.
Yeah.
Things like image recognition,
Right.
natural language processing,
Mhm.
even playing games like chess at a superhuman level.
Yeah, it's crazy.
All of these achievements are powered by neural networks that have been trained on massive amounts of data.
So they've essentially learned patterns and relationships within that data.
Exactly. And what this research proposes is that we can take that learned knowledge, that intricate understanding of the world that these neural networks have developed, and transfer it to a VQC.
So we're essentially giving the quantum computer a head start,
Yeah, and
like handing it a cheat sheet for the exam.
kinda, yeah.
Okay, I like it.
Instead of starting from scratch, the VQC can begin with a wealth of knowledge already encoded within it.
Makes sense.
Mm-hmm.
But what concrete benefits does this actually provide?
Yeah.
Does it make the quantum computer smarter somehow?
It definitely makes it more efficient,
Okay.
which is critical given those limited qubits we were talking about.
Right.
For example, it significantly reduces what's known as approximation error.
Approximation error.
Yeah.
What's that?
Think of it like this. With fewer qubits, a normal VQC might struggle to accurately represent complex data relationships.
Okay.
But with this pre-trained knowledge, it can achieve a much higher level of accuracy.
So it's like having a sharper lens to focus on the problem, even if the camera itself isn't that great.
Precisely.
Yeah, okay.
And it goes beyond just accuracy.
Right.
This paper outlines several really intriguing theorems about the advantages of this approach.
Okay.
Take theorem 1, for instance.
Okay.
It states that by using this method, the VQC's representation power actually becomes independent of the number of qubits.
Hold on. Independent of the number of qubits.
Yep.
But I thought we just established that having more qubits was like the whole point.
That's the conventional wisdom.
Okay.
But this research really challenges that assumption.
Interesting.
It suggests that we can, in a sense, sidestep the limitations of our current quantum hardware.
Now, that is a game changer.
Yeah,
But we still need data to actually train these quantum computers, right?
right.
Where does that fit into this picture?
That's where theorem 2 comes in.
Okay.
It highlights another key benefit of this approach.
Mhm.
Even with a limited amount of quantum data, the VQC can generalize well to new problems thanks to the knowledge it's inherited.
So it's like the VQC has already seen millions of examples through the pre-trained neural network.
Yeah,
So it doesn't need as much specific quantum data to learn new tasks.
exactly.
Okay.
It's a bit like teaching a child who's already learned basic arithmetic how to solve algebra problems.
Got it.
They can pick it up much faster because they already have a foundation of mathematical understanding.
So we're talking about faster learning,
Mm.
less reliance on those precious qubits.
Right.
This is starting to sound like a cheat code for quantum computing.
Yeah.
But how does this all play out in the real world?
Right.
Does this actually translate into tangible results?
Well, the researchers put this theory to the test in some really interesting ways.
Okay.
One example involved using this technique to classify quantum dots.
Quantum dots,
Yeah.
those sound familiar, but refresh my memory.
Sure.
What are those again?
They're these tiny semiconductor nanocrystals,
Okay.
Essentially, really, really small particles
All right.
that have unique properties because of quantum mechanics. Hmm.
They have the potential to be used as building blocks for future quantum computers.
Wait, so they use this quantum machine learning technique to help build better quantum computers.
Yeah.
That's like some kind of quantum inception or something.
It is quite a fascinating loop, isn't it?
Yeah.
The specific task was to classify these quantum dots based on their charge state,
Okay.
which is a critical factor in building stable qubits.
And I'm assuming this new approach proved to be more effective than traditional methods.
That's right. That's what's really cool about this research. It's not just limited to quantum dots. They actually applied the same technique to a completely different problem,
Oh, that could
analyzing DNA strands.
DNA. That seems like a pretty big leap from quantum dots.
Hmm.
How does DNA even factor into quantum computing?
Well, it might seem surprising,
Mm.
but at its core, DNA is essentially a quantum system, the way those base pairs interact, and the energy levels involved. It all boils down to quantum mechanics.
Okay, so I'm starting to see the connection.
Yeah. But what were they specifically analyzing in the DNA?
They focused on predicting binding sites on DNA strands.
Binding sites.
Yeah, these are specific locations where proteins can attach.
Okay.
And this binding process is super important. It plays a crucial role in regulating gene expression.
Ah, okay.
Understanding these binding sites is essential for developing new drugs and therapies.
So they were essentially using this quantum machine learning technique to probe one of the most fundamental processes of life itself.
Exactly.
Right.
And just like with the quantum dots, they found that this approach, leveraging those pre-trained neural networks, led to significant performance gains compared to traditional VQCs.
Nice.
Yeah, you can actually see these results in Figure 8 in the paper.
Okay, cool. I'll have to check that out. But before we get too carried away,
Sure.
I want to make sure I understand something.
Okay.
Earlier, you mentioned Theorem 3,
Right.
which talked about an exponential convergence rate.
Uh-huh.
What does that mean in plain English?
Basically, it means that the quantum computer learns much faster with this approach.
Okay.
It doesn't need as much data or as many iterations to find the optimal solution.
So it's like taking the scenic route versus finding a superhighway to your destination.
Exactly.
I like that. So it's not just about making the quantum computer smarter, it's about making it a faster learner as well.
That's right.
And that seems crucial, especially given the challenges of working with these delicate quantum systems.
Absolutely. Remember, we talked about decoherence earlier.
Right, that tendency for quantum systems to lose their quantum properties.
Yeah.
Due to interference from the environment, like the
Yes.
quantum equivalent of static noise.
Exactly. And decoherence is a major obstacle in quantum computing.
Yeah.
The longer a computation takes, the more likely it is to be affected by decoherence.
So anything we can do to speed up the learning process is a huge win.
Huge win.
Okay, so this approach is like a double whammy. It makes the quantum computer more efficient and helps it learn faster, giving it more time to work its magic before decoherence sets in.
Precisely.
Okay.
It's all about maximizing the potential of our current quantum hardware, while we continue to strive for more robust and fault-tolerant systems in the future.
Right?
And this research is definitely a step in the right direction.
Okay. I'm really starting to see the bigger picture here.
Yeah.
We're not just talking about incremental improvements. This could potentially revolutionize how we approach problem solving in fields like medicine materials, science, and even our understanding of the universe itself.
It really is a profound shift in perspective. Imagine a world where we can design new materials at the atomic level, creating things with properties we can only dream of today.
Like what?
Superconductors that operate at room temperature.
Wow.
Revolutionizing our energy grid.
Yeah.
Ultra-efficient solar cells that capture nearly all of the sun's energy. Making renewable energy truly limitless.
Okay, that would be a game changer for tackling climate change.
It would.
What about applications in medicine?
Yeah.
It feels like there's so much potential there,
Yeah.
but it's hard to even fathom what's possible.
Imagine developing personalized medicine tailored to an individual's unique genetic code.
Okay.
Identifying the most effective treatments with the fewest side effects,
Wow.
or drugs that target specific disease pathways with incredible precision, minimizing collateral damage to healthy cells.
So we're talking about not just treating diseases, but potentially curing them at their root.
That's the ultimate goal.
Yeah.
And quantum machine learning could help us get there by enabling us to simulate complex biological processes, like the folding of proteins, which is currently a major bottleneck in drug discovery.
Protein folding. That rings a bell. Remind me why that's so important again.
Sure, proteins are like the workhorses of our cells, and their function is intimately tied to their three-dimensional structure, how they fold into these intricate shapes. Understanding this folding process is key to understanding diseases like Alzheimer's and Parkinson's,
Okay.
which are caused by misfolded proteins.
So if we could accurately simulate protein folding, we could potentially design drugs that prevent these misfolding errors, or even correct them after they occur.
Precisely.
Oh.
It would open up a whole new avenue for treating these debilitating diseases, and that's just one example.
Right.
The possibilities in medicine are truly vast.
It feels like we're talking about a whole new era of scientific discovery, powered by quantum insights.
Yeah.
But could we push even further? What about understanding the universe itself? The big questions that have baffled scientists for centuries.
That's the ultimate frontier, isn't it?
Yeah.
Quantum computers could give us the tools to simulate the behavior of black holes, explore the nature of dark matter, maybe even test fundamental theories of physics in ways that are currently impossible.
This is all so mind-blowing. It's both exciting and a bit daunting to think about the implications. Feels like we're standing at the edge of something truly revolutionary.
It is a truly transformative time.
Yeah.
And as with any powerful technology, there will be challenges and ethical considerations to address.
Of course.
But the potential benefits are so vast,
Yeah.
so world-changing, that it's impossible not to be excited about the future of quantum computing.
Okay. I think we've covered a lot of ground here. We've explored the potential of quantum machine learning, delved into the technical details, and even touched on the ethical considerations.
Yeah.
But before we wrap up, I have one final question that's been swirling in my mind. If we can overcome these challenges and really harness the power of quantum machine learning, what's the ultimate potential here? What kind of problems, the ones that seem completely impossible today, might we be able to solve?
Well, think about problems that involve simulating complex quantum systems, like designing completely new materials from the ground up with properties we haven't even imagined yet.
So not just improving existing materials, but creating things that are fundamentally different at the atomic level.
Exactly. And we could design superconductors that work at room temperature,
Okay.
revolutionizing our energy grid,
Yeah, that would be huge.
or ultra-efficient solar cells that capture nearly all of the sun's energy, making renewable energy truly limitless.
Okay, that would be a game changer for tackling climate change.
Absolutely.
What about applications in medicine?
Yeah, medicine is a really exciting area.
It feels like there's so much potential there, but it's hard to even fathom what's possible.
Imagine developing personalized medicine tailored to an individual's unique genetic code,
Okay.
identifying the most effective treatments with the fewest side effects,
Wow.
or drugs that target specific disease pathways with incredible precision,
Okay.
minimizing collateral damage to healthy cells.
So we're talking about not just treating diseases, but potentially curing them at their root.
That's the ultimate goal.
Yeah.
And quantum machine learning could help us get there by enabling us to simulate complex biological processes, like the folding of proteins,
Right, protein folding.
which is currently a major bottleneck in drug discovery.
Remind me why that's so important again.
Sure, proteins are the workhorses of our cells, and their function is intimately tied to their three-dimensional structure, how they fold into these intricate shapes.
Right.
Understanding this folding process is key to understanding diseases like Alzheimer's and Parkinson's,
Okay.
which are caused by misfolded proteins.
So if we could accurately simulate protein folding, we could potentially design drugs that prevent these misfolding errors,
Yeah.
or even correct them after they occur.
Exactly.
Oh.
It would open up a whole new avenue for treating these debilitating diseases, and that's just one example.
Yeah.
The possibilities in medicine are truly vast.
It feels like we're talking about a whole new era of scientific discovery, powered by quantum insights.
It really is a paradigm shift.
But could we push even further? What about understanding the universe itself? The big questions that have baffled scientists for centuries.
That's the ultimate frontier, isn't it?
Yeah.
Quantum computers could give us the tools to simulate the behavior of black holes,
Okay.
explore the nature of dark matter, maybe even test fundamental theories of physics in ways that are currently impossible.
This is all so mind-blowing.
Yeah, it's pretty amazing.
It's both exciting and a bit daunting to think about the implications. It feels like we're standing at the edge of something truly revolutionary.
And remember, this is just the beginning.
Right.
As quantum computers become more powerful and we develop even more sophisticated algorithms, who knows what incredible breakthroughs await us?
Well, on that note, I think it's safe to say that we'll need a few more deep dives to really wrap our heads around all of this.
Yeah, yeah.
But this has been an incredible journey. We've gone from the nuts and bolts of qubits and quantum circuits to the mind-boggling possibilities of a quantum-enhanced future.
It's been a pleasure exploring these ideas with you.
And to our listeners, if you're as intrigued by the potential of quantum machine learning as we are, we encourage you to check out the links to the research paper and other resources in the show notes. There's a whole universe of information out there waiting to be explored.
And remember, the quantum world is full of surprises. Keep asking questions, keep learning, and keep diving deep.
Until next time, stay curious.